All right, this is baby real analysis, and in this set of videos, I'm going to focus on integration. So that's why it says integration series. So this is part of the baby real analysis YouTube playlist, and yeah, the topic for these set of videos is integration. And so what we're going to start with is the Riemann integral according to Bartol's Intro to Real Analysis 4th edition textbook. And then we're going to go into the, I don't know how to pronounce this, Darboux form of integration as presented in Bartol's text and also in Jay Cummings' textbook, Real Analysis, Long Form Mathematics textbook. And then we're going to establish that the Riemann and Darboux definitions for integration are equivalent. That is the goal for these set of videos. All right, so the Riemann integration according to Bartol. Now suppose we have, and this is also assuming you're familiar with what an integral is. Now let's suppose I have some curve, and let's say that's my curve, and I define it on an interval. Let's say the interval begins at 1 and ends at 4. And I want to know what is this area that's underneath the curve within that interval. So I want to know, what is this? All right, and Riemann decided that you can approximate this area using rectangles. All right, and you can slice up the overall interval into subintervals. So let's say I partition it, is the word, partition the interval 1 to 4 as follows. So I just choose some slices of my interval, and these subintervals don't necessarily need to have the same length. In calculus, they treat it like they do have the same length. So these subintervals, let's say this is the first one, second one, third one, and then let's say those are my ways that I'm slicing it up. And then if I wanted to find the area, I can use a rectangle from each sub-interval. And I would do that using rectangles. So like for the first sub-interval, I would go from, let's say I use the left endpoint. So the left endpoint touches there on the curve, and I just go straight across like that. And so I'm kind of over approximating it. Now for the second subinterval, let's say I again use the left endpoint. And let's say for the next one, I choose to use the right endpoint. And again, let's say I did the right endpoint. And last, again, let's do the right endpoint. Now, so I've broken up in these different rectangles, and each rectangle has a certain length or width and a height. And to get the heights of the rectangles, I choose a value in that subinterval. So what we did was we partitioned our interval 1-4, and then we picked an endpoint or picked a value in each subinterval. to evaluate to get its height of the rectangle. And for this value that I pick, it doesn't matter which value you pick in the subinterval, actually. So it doesn't matter what you pick for the value in each subinterval when you use an infinite amount of rectangles. Okay, so I wrote it doesn't matter what you pick for the value in each subinterval when using n number of rectangles as n goes to infinity. And the widths of each each rectangle, which is the length of each subinterval, can be anything. So the widths don't have to be the same for the rectangles. Okay, so that's sort of the idea, is I slice up my interval into subintervals. I pick a value from each subinterval, evaluate the function for that value in each subinterval. That gives me the height of the rectangle. And I do that for all of the subintervals, and then I sum up the rectangles. And that'll give me an approximation for the area. Now, the more number of rectangles you use, the better the approximation. In fact, when you use n number of rectangles as n goes to infinity, you get the exact area. Now, that is the process. So now, I'm going to go into like some formalizing the language. So some definitions. So we talked about a partition. So a partition P is a choice for where you have A is going to be your x naught, which is less than x1, less than x2. And by the way, we're dealing with real numbers, so we're dealing with partitions as intervals, dot, 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 and then less than xn, where xn is b. So you partition an interval, slice the interval up into subintervals for your overall interval is AB. Now for each subinterval, so that's what a partition is. So for each subinterval, of the form x subscript I minus 1, comma x subscript I, you're going to choose a point, ti, in that subinterval, and these are going to be called the tags. All right, so that's partition, and we slice it up into subintervals. For each subinterval, I choose a point ti, and that ti value is called a tag. And we're going to use the tags to determine the height of the rectangle. Okay, so your height h is equal to the function f evaluated at your tag ti, the base of the rectangle. Base b is equal to the length of the integral, so it's equal to xi minus 1. All right, so that's the base. So then the area of one rectangle so we know area is base times height. So that's equal to base times height. And that's going to be equal to our height is f of ti times the base, which is xi minus x subscript I minus 1. All right, that gives us the area of one rectangle. Now, if we want the area of all the rectangles, that's going to be denoted as S, and then parentheses, you have F, semicolon, and then P, and it has P with a dot over it. So the P with a dot over it means it's a tagged partition. So you partition the interval, you pick your tags. So this notation is going to be representing the sum from I equals 1 to n of the base times the height of the rectangle. So it'd be f of ti for the height times xi minus xi subscript I minus 1. So that's going to give you the area of the rectangles. Now another definition is the norm. So the norm, which is denoted as, so the norm of the partition P is notated as this. So it has two lines like that. It looks like kind of like an absolute value, but it's equal to the max of the absolute value of xi minus 1 from I equals 1 to n. So I is, so 1 is less than or equal to I, which is less than or equal to n. So that is what the norm is. It's the greatest length of the subintervals. So now we're going to go into the function being Riemann integral. So definition, a function f is Riemann integrable on some closed interval ab with integral L if for all epsilon there exists a delta dependent on epsilon. So I'm calling it delta subscript epsilon, but there exists a delta greater than 0 such that if P with that dot over it is any tagged partition, so this applies to all tag partitions. So if that's any tag partition with the norm of this tag, any tag partition being less than delta, then the absolute value of our Riemann sum thing, so our S of P minus L is less than epsilon, where L is denoted as this symbol, the integral symbol a to b of f. All right, that is what it means for it to be a function to be Riemann integrable. So the delta epsilon is dependent on epsilon. One thing to note is that the norm is not a function of the Riemann sum. So that is, this limit is a different type of limit than what we're used to. So some texts you'll see the norm approaching zero as some limit. But this limit isn't the limit that we've been talking about in regards to functions, as the norm is not a function of the sum, but our norm is not a function of the sum. Okay, so that's something to make note of. So this is basically a different type of limit than what we've been dealing with in the previous videos of this course. But the delta, regardless, still depends on epsilon. All right, so those are the definitions. And again, so we have a partition P. It is a choice of slicing up the interval, and our interval is A, B. And each subinterval xi minus 1 to xi, you choose a point ti. That ti is called a tag. You use the tags to determine the height of the rectangle, where the height is given by f of ti. And the base is the length of each subinterval. And so you sum up these areas in that Riemann sum, and then further we have the norm is the length of the largest subinterval. And so a function is Riemann integrable with integral L if for all epsilon there exists a delta such that if P is any tag partition with the norm being less than delta, then the absolute value of the Riemann sum minus our integral L is less than epsilon, where L is the integral AB of f. All right, so now I'm going to go into two examples, and we'll show that these two examples are Riemann integrable. And then I also made this note that you'll see the notation of the norm shrinking to zero. So the norm basically tells us how skinny the rectangles should be. All right, so here's our first example of showing something is Riemann integrable. Say I'm given the function f of x is equal to 4. Let's check that it's Riemann integrable. So it's a constant function. So it's going to be a horizontal line. So check that this is Riemann integrable. On the closed interval 2 to 7. All right, so that is our example that we're going to do, just to visualize. So we basically say this is 2, this is 7. Let's say 4 is right here. So basically, this is our function. This is horizontal line, and we're specifically focusing on going from 2 to 7. And we're going to check that it's Riemann integrable. So the thing is, with our definition for Riemann integrable, is I need some value L, right? So the definition requires me to know what is this value L. So that is the caveat to this. So I claim that L is equal to 20. So I need to prove that claim. All right, so I have the interval 2, 7. So I'm going to partition it in any way. So if I pick any tag partition, all right, so there's 2, this is 7, so like 2 is my x naught, 7's x in, and then I'm slicing it up, x1, x2, x3, and so forth. Let's say I get to the ith one, so that's xi plus 1, dot, 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 and then we get down to xn minus 1, and then xn. And so I choose a tag, pick a tag from each of these. So like maybe it doesn't matter whether I use the left endpoint, right endpoint, or anything in between. So like I could choose this as a tag, this as a tag, this as a tag, and then so forth until I get to all these values. So I'm picking a tag partition, so these are my tags. All right, so let ti be the tag for each subinterval. So x subscript I minus 1 to x subscript I. All right, so let ti be the tag for each of those. So we know our function gives us 4 for whatever value for x. Since f of x equals 4 for all x in 2 to 7, then f of ti is equal to 4 for all our tags. So when we find the Riemann sum, so S and then F with our P, that notation, the sum equals I to N of F of Ti times Xi minus 1. We know that our function evaluated for each tag is 4, so that's equal to 4 times Xi, then Xi minus 1, from I equals 1 to N. And then that's equal to 4 times the summation of the xi minus 1. So this will be equal to 4. And then you just, find the sum is, so like when I is 1, that's going to be x1 minus x naught plus x2 minus x1 dot, dot, dot. And then until you get to the nth one, so it'll be plus xn minus xn minus 1. And you'll see that all the values collapse. So like x1 minus x1, x2 will collapse, and then all of them collapse except for xn and minus x naught. So this is equal to 4 times xn minus x naught. Well, that's our endpoints to the original sub interval 2 to 7. So xn is 7, x naught is 2. So this would be 4 times 7 minus 2. So that's 20. So our Riemann sum is equal to 20. So no matter what our partition is, we have that we do the Riemann sum minus our integral L is equal to 0. So that's going to be less than epsilon, because our choice for L was 20. All right, so that's just a simple example of a constant function on some interval 2 to 7. And so we got that to be Riemann integrable with our integral L being 20. And so we just partition the interval, pick a tag, evaluate the tags. That's going to get 4 for all of them. And then take the summation. The summation came out to be 20. And our integral L that we claimed was 20. So then that's why we get 20 minus 20, which is 0. That's certainly less than epsilon for any epsilon. Okay, so that is that example. I'm going to do one more example for this video. Say I give you a piecewise function, and that piecewise function is broken up into 2 pieces, where the top piece, f of x is equal to 3, if x is not equal to 1, and then it's equal to negative 4, if x does equal 1. Now, the question is this Riemann integrable on 0 to 2? All right, so that's the question. Now, what does this function look like? Let's say that's 3, negative 4. So it's going to be equal to 3 for all values that are not equal to 1. And our interval is going from 0 to 2. So let's say this is 2. And then this is 1. Okay, so everything is equal to 3. And then it jumps at 1 down to the point right here, negative 4. And then jumps back up. And that's our function. So we are going to show that this is Riemann integrable on this closed interval 0 to 2. All right, so we slice up our interval. Partition 0, 2 to any tag partition. Now the question is, like, because we have a value that's different from the rest of them at a particular value 1. So like before, it wouldn't be a problem if this was already filled in, because this would be just like our previous example. We just do all that like before. Now, because it does have a hole at that value, it is possible that one of our tags is chosen to be at 1, and if it's at 1, then the height of it will go down to negative 4. So that is where things get messy. So if one isn't a tag, it's simple. So we have our partition. All right, and the question is if one isn't a tag, is this fine? All right, so let's say, so case one, let's say one is not a tag. All right, so if one is not a tag, then we're fine because we just choose anything in each subinterval, then evaluate it for these tags. Since they're not equal to 1, then since ti is not equal to 1, that means the height f of ti is equal to 3, since they're not equal to 1. So f of ti is equal to 3, which means that our Riemann sum that's going to be equivalent to the sum of 3 times xi minus 1, which we know is in the previous example, we know it collapses so that it's 3 times and then xn minus x naught. And that in this case are xn and x naught. So x naught is 0, xn is 2. So it'd be 3 times 2 minus 0. So 6. All right, so that's our Riemann sum. Is equal to 6 if there's no tag that's chosen to be 1. All right, so then I would just use L as 6. And then you'll have S of F P minus L, which is 6 minus 6 is equal to 0, so that's less than epsilon. All right, so we're fine when none of the tags are 1. The problem is what happens when 1 is a tag. So what happens now, just keep it in mind, like, so if we have our partition, it is possible that we have 2 intervals, namely that, let's say this interval, and we use 1 as a tag for that interval. So 1 is a tag for that, so that'd be the right endpoint of that interval. And then the following interval, we still use 1 as a tag, but it'll be a left endpoint. And so we could have 1 being a tag twice as the maximum number of ways in which 1 could be a tag for this partition. So the max number of ways, max number of tags for 1 to be is 2. All right, so let's say this is subscript xk minus 1, and then 1's at xk, and then this is xk plus 1. So it's possible that for our kate, we have an interval where it's xk minus 1 to xk, and then xk to xk plus 1, where 1 is xk. And so this would be like doing the kth tag is 1, and this would be the k plus 1 tag is also 1. It's possible to have that. So this could be like our worst case scenario. I was trying to think of what's the maximum number of tags we could have to be 1 possible. And that would be if it was used twice as a left endpoint or as a right endpoint, and then as used as a left endpoint for 2 subintervals that are right next to each other. All right, so first I'm going to handle the case in which we just have 1 being a tag for one of the tags is 1. So now that we've established, yes, it's possible 1 could be a tag. It could be at most 2 tags. What happens when 1 is exactly 1 tag? So we covered case 1 where 1 is not a tag. And then that came out nicely because that's like our constant function example before this. Now we're going to handle what happens when 1 is a tag. Well, it could be 1 tag could be 1, or 2 of the tags could be 1. So I'm going to handle the case where 1 of the tags is 1. So exactly 1 of the tags is 1, just to see what does it look like when you find the sum. All right, let's say tk tag tk is 1. Well, what do we do for when the function evaluated at tk? So that means f of tk, when the value is 1, our function is equal to -4. So f of tk is equal to -4. So what does the sum look like? So we do find its sum. Just showing what it would be. So for all values that are not this particular tk value, so for all ti that are not tk, f of ti is equal to 3, right? Because that's 3 for all values that are not 1. So we could say this is essentially equal to 3 times and then x1 minus x naught plus 3 times x2 minus x1 and so forth. It's only until we get to the kth, so where tk is, so at that particular subinterval, we're going to have -4 times, and our tk tag comes from the interval xk minus 1 to xk. So it'll be -4 times xk minus xk minus 1. And then it's 3 for everything else. So then plus 3 times xk plus 1 minus xk and so forth. All right, so how am I going to find this particular sum? All right, so we know that if this spot right here, we know that if this was a 3, we know that the sum is 6. All right, but what I'm going to do is a little trick, our usual math trick, is to add 0. So the trick we're going to add 0 So we can make use of our sum being 6. So we're going to add 0 in the form. Well, it would be convenient if this value, -4, was a 3. So I'm going to add 0 in the form of 3 times xk minus xk minus 1, but then I have to subtract it. So then minus 3 times xk minus xk minus 1. All right, and now I can pretty much find our sum by adding 0 like this. So I'll do that as follows. So how is this going to look like? So our sum, so we have 3 times x1 minus x0 plus 3 times x2 minus x1 plus ... Now I'm going to use this part, so plus 3 times xk minus xk minus 1, then plus 3 times, xk plus 1 minus xk plus ... and then plus 3 times xn minus x0. So that's all 6. But then I still have this part and then the minus 4. So then I still have this plus -4 times our xk minus xk minus 1. And then I have this still, and then now a -3. All right, so all of this stuff is, all the stuff in blue is 6. So this will all equal 6, and then the stuff in red, which we have -4 times something and plus -3 times the same something. So they're like terms, so that makes -7. So it'll be 6 plus -7, or 6 minus 7 xk minus xk minus 1, which we know is a little bit less than 6. All right, that is what our sum would turn into. So our S of Fp is equal to 6 minus 7 at what we have in red above. When we have one of the tags is 1. Now what happens when you have 2 of the tags be 1? So exactly 2 of the tags are 1. All right, let's say their tk is 1, and then tk plus 1 is also 1. That means f of tk, -4. F of tk plus 1 is also -4. You can do the same argument as above. Or logic. We'll get that the sum is going to be equal to 6, and then minus, so it'll be like this case too. So we have the minus 7 times xk minus xk minus 1. And then now, since there's 2 tags, then we can, it'll be another minus 7, but this time it's the next interval, subinterval that it's coming from. So it'll be xk plus 1 minus xk. All right, so you do the same argument as the second case. You're just going to add 0 again in a different form, manipulate it, so you get the sum to be 6, and then minus these 2 terms. All right, so that is, which we know is less than the previous case, but that is what it looks like for these two. And so we want our definition to work for any epsilon. So pick epsilon greater than 0. We're going to choose delta to be epsilon over 14. So then that means the norm is less than delta, which is less than epsilon over 14. All right, and so these links are going to be less than epsilon over 14. So the length xk minus 1, that's less than epsilon over 14. And xk plus 1 minus xk is also less than epsilon over 14. All right, and I'm going to say that my integral L is 6. So L is 6. And what are we trying to show, right? So we need to show that the absolute value of the Riemann sum minus L is less than epsilon. Okay, well now L is 6, and then my sum, and we'll show that we'll eventually get to this. So this sum part right here, 6 minus 7 times that length times the other one, it's actually going to be greater than the length of, so when I do 6 minus epsilon over 14 minus another epsilon over 14, that's less than, so 7 times that, sorry. Back up again. Okay, so I'm trying to say that this portion, so since this is epsilon over 14, is a bigger amount than the length of these two values, where I do xk minus 1, and then xk plus 1 minus xk. So since that's the case, I'm doing 6 minus a bigger value would be, that difference is going to be smaller than the difference of 6 minus the other value. So for instance, I'm saying like 6 minus 2, that's like less than 6 minus 1, for example. So I'm saying that this 6 minus 7 times epsilon over 14 minus 7 times epsilon over 14, that is less than 6 minus 7 times xk minus xk minus 1 minus 7 times xk plus 1 minus xk. All right, that itself, and that's basically our Riemann sum. So this is less than or equal to S of Fp, which we know that the largest this is going to be is less than or equal to 6. So I can go ahead and say all that. So again, this portion, I'm doing 6 minus a bigger number is going to be less than 6 minus smaller number, because each of these xk minus 1 is each of those are going to be less than epsilon over 14. And so that difference that I have on the left is a smaller difference than the next inequalities. But then that inequality is basically my Riemann sum. That's less than or equal to S of Fp, where P is partition, and that's less. We know that maximum of that was 6 when 1 was not a tag, so that's less than or equal to 6. All right, so hopefully that logic makes sense. And what do we have? So combining the left sides, so these 7, so that's like 6 minus epsilon over 2, and then minus another epsilon over 2, so that's 6 minus epsilon is less than my Riemann sum S of Fp, which is less than or equal to 6. All right, I just skipped writing this part and just wrote, going from the next line to below, just the leftmost portion is 6 minus epsilon, and then they less than or equal to the summation part, which is this, that's 6 minus, or this, I basically just skipped writing that part to make it a little bit more condensed. And we know that sum's less than or equal to 6. So we can subtract 6 from everything. So that's if and only if negative epsilon is less than our summation, Riemann something, minus 6, and then subtracting 6 from 6 is less than or equal to 0. All right, well, certainly for any real number that's bigger than 0, so this would be less than or equal to 0, which is less than any positive number epsilon. So we have negative epsilon less than our summation, minus 6, less than epsilon for all epsilon. Well, what does this mean? That's if and only if the absolute value of our summation, minus 6, is less than epsilon, which is what we needed to show. All right, so that worked when our delta was chosen to be epsilon over 14. All right, that's the delta that works, that made this proof work out. All right, so hopefully that made sense. It was a little tricky in the sense you had to think of how would you add 0 in what form, and think of the, I guess the worst case scenario would be 1 is 2 tags, and then from there choosing your delta appropriately for that kind of case. All right, so that's where I'll end it for this video, and next video I'll go into just more theorems and definitions with the Riemann integral. I just wanted to show 2 examples.